So now that we've learned about finding and classifying extreme intervals, we can move on to one of the first major applications, like actual applications of calculus, and that's to optimization. In other words, making something as large or as small as possible. So in this lesson, we're basically going to learn and really just practice how to solve problems that ask us to optimize a quantity. But as always, before we do that, let's take a deep breath. And now let's begin. So truth be told, I don't know that there's really much new knowledge to be gained in this lesson. We're really just practicing this finding maximums and minimums and now putting those problems into a context. I suppose the one thing I might mention is just this idea of optimization or optimizing something. When we optimize something, it basically means to make it the best, right? We want to optimize something. When we want to make something the best, either that we want to make it the largest or the smallest that quantity can possibly be. So people might decide that if you want to optimize the cost of something, well, for cost, we generally want it to be low, and so an optimized cost might be a smallest value. Whereas with something like profit, yay capitalism, profit, if we want to optimize that, we want our profit to be as large as possible. So when we're optimizing something, we're generally going for being the largest of something or the smallest of something. Generally speaking, problems are going to tell us whether they want us to find the largest or the smallest value. So you're usually not going to have to figure it out for yourself, but when you do, it should be self-explanatory, and you should be able to figure out which one they're looking for. So this first example that I have says the height of a swing h in meters at a time t seconds is given by this function, h equals 2 minus 1.5 t squared. For 0 less than or equal to t less than or equal to 3, find the minimum and maximum height of the swing. Now, when I took this problem from a textbook, and when this was given in the textbook, they had it as an open interval. They went 0 less than t less than 3. And I found that to be sort of troublesome because some of the answers that they actually got were either 0 or 3. I don't think that we're going to see that happen on the IB exam. I think that generally they're going to refer to a closed interval and expect it to be as such. So I'm generally going to be setting these problems up with closed intervals. And the nice part about that is that it references sort of the theorem or the key point that we learned yesterday, where if you have a closed interval and a function that's continuous, you are guaranteed to have a maximum and a minimum that happen on that interval. So with that said, we're really solving this word problem the same way that we did the problems in the previous lesson. We're going to remember that our maximum and minimum will either happen at the stationary points or they'll happen at the endpoints in the interval. So the first thing we need to do is we need to find out where are the stationary points. So I'm going to start by taking the derivative. H prime will be, now the derivative of this, the derivative of 2 is 0, so okay, 0. And the derivative of sine is cosine. So this will just be negative 1.5 cosine t. Now we want to know where this is 0 or undefined. It's not undefined because cosine is a nice continuous function. So I just set it equal to 0. 0 equals negative 1.5 cosine t. I can just divide that 1.5 over to the other side and get that cosine t is 0. And now we just need to sort of pause and think for a moment. On this interval, where is cosine 0? Well, cosine is going to be 0 when t is pi over 2. And so now we've found our only stationary point. Our only stationary point is at pi over 2. And then what we need to do now, remember from our lesson yesterday, now that I have this stationary point and this interval, how am I going to find the minimum and the maximum values of the height? Well, all I need to do is take my stationary value and my endpoints, my interval, and plug them into this thing. So I just need to compute what is h of 0, what is h of pi over 2, and what is h of 3, and look at which one of those is the smallest and which one is the highest. So h of 0 is going to be 2 minus 1.5 sine of 0, and the sine of 0 is 0, so this whole second part vanishes, and so the height at time 0 is 2, so 2 meters. We have no idea if that's a highest or a lowest, but that's our first one. Now we go on to pi over 2. For pi over 2, I'm going to have 2 minus 1.5 times the sine of pi over 2, and we know the sine of pi over 2 is 1, So 2 minus 1.5 times 1, this is going to be 0.5 meters. Okay, so now we can definitely tell that this first one is not the minimum, and this one is not the maximum. The question is really just, when I use 3, am I going to get something that goes above or below one of these values? So let's find out. 2 minus 1.5 times the sine of 3. Now, this is interesting. 3 is not a unit circle value, which means either we need to use the calculator for this, or I really believe that this could be a non-calculator problem. And the reason that I say that is, if you think about where 3 is on the unit circle, right? This is 0, this is pi over 2, way over here I have pi, and remember pi is going to be like 3.14. So an angle of 3 is going to be like here-ish or something. And so the sine value is going to be some small positive number, right? And so you can sort of imagine that this is going to be 2 minus 1.5 times, and I'm not really sure what this is. Maybe it's going to be like 0.1 or something. Can you see, though, that this is definitely going to be smaller than the 2, but also bigger than the 0.5? So even without a calculator, I can tell that this one is not going to be one of the extrema, right? So at the end of this, I've compared all of these things, and I can see now that the maximum height of the swing is going to be 2 meters, which is a little over 6 feet. So depending on the playground you're on, that's either high or not that high. And then the minimum height is going to be 0.5 meters. And that's the end. Like that's the process. So I used my, absolute maximum minimum thing, and I put that in a context, and then I answered sort of using that context. This next example is different than the first one was, and we're definitely going to get more practice with these later. I wanted to put one weird one in the middle while you still had a good amount of brain power left, where I'm not giving you the function that needs to be optimized. Sometimes you're going to encounter these problems where you need to really sort of build the problem on your own. So with the way that this one's going to work, right, is we're being asked to find the maximum product of two positive numbers whose sum is 20, right? So find the maximum product. So it's almost like we've got some p function, p for product. Maximum product of two positive numbers. So p is going to be x times y. And that's the thing that we want to optimize. This is the thing that we want to take the derivative of and set equal to 0 and do all of that for, right? The trouble is we've never done this when there's been multiple variables over here. So there's got to be more information in the problem. There's got to be something out there somewhere that I can use to reduce the number of variables that I have here. And this is really going to come down to kind of being like a system of equations, right? What other equation could I come up with when the problem says two positive numbers whose sum is 20? Right? What relationship could I get between x and y? And hopefully you recognize, we could do something like x plus y has to equal 20. But if I know that x plus y equals 20, wouldn't that mean that that y is equal to 20 minus x? And so if I know that y equals 20 minus x, we can take that and put it in over here. And so instead of having p equals x times y, we could have p equals x times 20 minus x. Right. And now I've got this thing in a way that's, it's a single variable, it's something that I can work through. I suppose the only thing I might want to do is maybe simplify this a little bit before I take the derivative. But now this is the thing that we want to optimize. I want to optimize p. And so since that's the thing that I want to optimize, I want to optimize the product. I'm going to take the derivative. So let's see here. This will be 20 minus 2x, and that'll equal 0, because I'm supposed to take the derivative and set it equal to 0. Now when I solve this thing, I wind up finding out that 20 equals 2x, which means x has got to be 10. And so what we found here is we effectively found one of the stationary points. Right, we found a stationary point, but remember that our maxes and mins can happen at a stationary point or at the endpoints of the interval. And this problem didn't give me an interval. So I think maybe a question that I would ask, now that we've got a sense for what these numbers are, right? X and Y are these two numbers, these two positive numbers whose sum is 20. Do I have any boundaries on X? Is there any number that X has to stay bigger than, or that X has to stay smaller than? and I would encourage you, pause the video and think about the statement of the problem for a moment. Is there any limit on how small x can be? Yeah, x has got to be positive, right? So x has to be greater than or equal to 0. In fact, if it says positive numbers, x can't even quite be 0. But we'll sort of leave that in there for the moment. And then for the maximum, x can't be bigger than 20, because if x is bigger than 20, my other number would have to be negative so that they could add up to 20. So I've basically got x equals 10 is one potential place that I could have this maximum product. X being 0 is another possible one, and x being 20 is another possible one. Right? So now the last thing that I need to do is take these values and plug them back into my product function to figure out which one is going to give me the largest product. Right? So I could do the product of 10. That would be 10 times 20 minus 10. That's 100. I don't know if that's a max or min, but there it is. I could do P of 0, which would give me 0 times 20, which is a product of 0. Or I could do P of 20, which would give me 20 times 0, which also gives me a product of 0. So these two right here seem to be the minimum value that I could get. And this one here seems to be the maximum value that I could get. And so the answer to my question is that the largest possible product of two positive numbers that add together to be 20 is 100. So you can probably see here that the algebra, the actual computation that you had to do in this problem was easy. The challenge was in setting the thing up. So there will probably be one or maybe two of these problems in the assignment today, and we will practice more of these if we're going to get into ones where you need to write your own functions. For this last example, we're going to be coming back to a little bit more straightforward of an optimization problem, a little bit more like the first example that we did. So for this one, you're told that a water bottle is being filled such that the volume of water in the bottle in ounces, V, at time t, measured in seconds, is given by this equation, and we're given an interval where time has to be between 0 and 10, in this case seconds. Okay? So parts A and B actually don't require any calculus at all. They're just a matter of sort of interpreting what the problem is talking about and what it all means. So I definitely encourage you to do parts A and B on your own. Make sure that you're making sense of what it is that we're looking at. So for part A, how much water is initially in the bottle? Well, we're told that this is happening between times t being 0 and 10, and so initially we'd be looking at time 0. So if I take t being 0 and plug it in, v of 0 would be 1/40 times, 20, 0, minus 0, basically a bunch of 0 plus 7. It looks like initially it's 7 ounces of water that are in the bottle. Now, some of you may be wondering, do you need to write down units? If the problem does not make a specific mention of, how much water is in the bottle, indicate correct units, then there's not going to be any points associated with units. It's a good habit to be in, but it's not strictly required because the problem didn't ask for it specifically. Part B, after 10 seconds, the bottle is full. What's the capacity of the bottle? Really same kind of thing as is happening in part A. We're just plugging in 10 and seeing what we have. So this would be 1/40 times 20 times 100, that's 2,000, minus 1,000, plus 7. So this is 1/40 times 2,000 minus 1,000, that's 1,000, plus 7. 1/40 times 1,000 is 25, and 25 plus 7 is going to be 32. So 32 ounces is the full capacity of the bottle. This, by the way, is not a statement that a 32-ounce bottle is better than a 40-ounce bottle. This is really just like this. This is the context that was set up on the problem. And if you ask me, the 40-ounce bottle is better. I really want to make sure I have as much water as possible to stay hydrated. But again, it's sort of outside of the context of the problem. So we've got part A, we've got part B, we've got these things. There hasn't been any calculus yet. There hasn't been any optimization. So we're expecting that to happen in part C. So it says, at what time is the water flowing into the bottle at the greatest rate? So I think the question that I want to ask you here is, what's being optimized? Like, we see the word greatest here. So what is it that they want to be greatest? What is it that they want to be largest? Hopefully you recognize it's not V, because we basically did that in part B. In part B, we found that the greatest amount of water that we could have is 32. So they're not asking when the volume is greatest. It says at what time is the water flowing in at the greatest rate. In other words, they want me to maximize the rate, V prime. right? So to maximize the rate, I first need to find the rate. So what would v prime be? I guess to get v prime, it would be nice if I sort of expanded this a little bit. So let's write v as, let's see, if I distribute that 1/40th in, I'll get 1/2 t squared minus 1/40th t cubed plus 7. So that's what v is. Now v prime, the derivative of that, will be, if I bring the 2 down, t minus 3/40ths t squared, and then the 7 is just going to vanish. And now if I want to maximize this thing, I need to take the derivative of that and set it equal to 0. Right? So my second derivative here will be 1 minus, when I bring this 2 down to take the derivative, this will be 6/40ths or 3/20ths t. And remember, in order to optimize this thing, I'm going to want to set this equal to 0 or look at when it's undefined. It's not ever going to be undefined. So I'm just going to have 0 equals 1 minus 3/20ths t. Okay. Working on solving this, I can move this over. 3/20ths t equals 1. So it looks like one of the time candidates is 20/3. But how do I know that this is the greatest rate? This could actually be the lowest rate. How do I figure out on this interval when the largest rate is versus the smallest rate? And the answer is we need to use that same process that we've been using all along. I need to test what is the rate at 0 and what is the rate at 10. I need to look and see which of these three things is going to yield the largest rate. Right? So I'm going to take all three of these things and what am I going to plug them into? Remember, what am I optimizing here? The thing I'm actually optimizing is the derivative. That's the thing that I want to optimize. That's the thing that I took the derivative of and set equal to 0. This is the thing that I want to be greatest. So that's the thing that I need to plug all these values into. So v prime of 0 looks like it's going to be pretty easy. V prime of 0 is just 0. V prime of 10, see if I plug 10 into that thing up there, I'd have 10 minus 3/40ths times t squared, that's 100. Let's see, I can reduce this a little bit, right? The 40 and the 100 would reduce down to 10. That would give me 30 over 4. So this is 10, whoops, not equals, 10 minus 30 over 4. 30 over 4 is 7.5. So this is 2.5. Okay, so I've got a 0, I've got a 2.5. Now really all I need to do is check for this 20/3. So what is v prime of 20/3? Well, let's see here. It would be 20/3 minus 3/40ths times 20/3 squared. I think it might actually be easier for me to just write 20/3 twice, because I can see this is going to cancel. This 20 is going to reduce this down to a 2, and that 2 will drop this down to a 10. So this is looking like 20/3 minus 10/3. That's 10/3, which is 3.3 repeating. So this one is the maximum rate. But remember, I wasn't looking for the maximum rate. They wanted to know, when does this happen? I'm actually going to go back and double check that. Yep, this question says, at what time is the water flowing in at the greatest rate? So the answer to my question is that the water's flowing in fastest when the time is 20/3.